Go ahead.
Okay, good morning everyone. My name's Katrina.
I'm Richard.
I'm Mamet.
I'm Sylvester.
I'm off the tree.
And this week our team worked on estimating the above ground biomass in the Bonanza Creek Experimental Forest. This forest is located in interior Alaska, and basically the forestry industry is really interested in being able to quantify the amount of carbon that is within these forests. And the best variable that they have to be able to quantify this is the above ground biomass. And so at the beginning of the week we were given data that had plots that had the AGB at these different sparse plots. And so our goal was to create a continuous map of the predicted AGB for the forestry industry's aid.
So we had three types of data. First was the plots that she described, and that was taken on site. Next we had the G-Light LiDAR plane data, which was recorded by a plane flying over the forest. And lastly we have the Landsat data, which is a satellite image of the entire forest.
I'm just going to go over a brief overview of the steps we took in order to get to the last model that we have, or the map. So first off, of course, we needed to explore the data that we had. We had 3 different sources, so we had to compile all of them into one big data set and start singling out the variables that were going to be the most significant. And on that note, we started looking for relationships and correlations among the variables, specifically which ones had a positive correlation with above ground biomass that would be the most helpful. And then we started coming up with simple linear models in order to get a general idea of the trend of where most biomass is concentrated and the least biomass is concentrated. And then slowly but surely we started designing and implementing more complex models until we were able to finally visually show a map with our estimated biomass values. So here I just listed all the relevant variables that we had from the start. Of course, we were going to slowly start taking out some variables that didn't make sense to use. So first off, we had the P10 through 100 values. So these were percentile height values, and they corresponded with how high the specific plot of land was, or the highest tree of the specific plot of land was. Next we had tree density, which, as the name suggests, is the amount of tree in a specific plot. Basal area is the cross-sectional area of the tree taken at 4.5 feet. Brightness, greenness, and wetness, you can see the 3 maps there. They're taken from satellite. So we have values for the whole forest, and their brightness, greenness, and wetness. So they're going to be helpful in expanding out the model in order to cover the whole area. The land cover type just simply describes whether it was over open water, a deciduous forest, evergreen forest, etc. The percent tree cover was another satellite image, which is on the bottom right there. And location was also an important variable when considering spatial models. So now we're just going to narrow down the specific predictor variables that we would use for biomass. So tree density and basal area were already on the plot land, which we already had the biomass values for. So they weren't going to be necessarily a predictor value since we already had them at the same areas. P90 and P100, they both had strong correlations with above ground biomass, and they're measured in a larger area due to being measured with LiDAR and the plane trends that you guys saw earlier. And likewise, brightness, greenness, and wetness all covered a much larger amount of land due to being on satellite and covering the whole area.
So we started out with with simpler models than what we ended up with, because a simplified model can be used to prevent skewed results, and it also shows why we need a more complex model, which is because simpler models can vary an answer because not all the data is considered, and instead of using all the data we can, approximations are made. Up here I have an example of a really simplified model where it's just adding up the AGB of the plots and multiplying that out to reflect the full forest size.
And here is another actual plot of a really simplistic model that just basically used the AGB models and spatial modeling in order to reflect it over the total amount of land. This was based on the Colorado data tutorial provided by Doug, actually. So that was really helpful in order to get us a starting idea of what our graph should look like. So as you can see, it's really inconsistent in that there's some points that have extremely high AGB values, yet they're in shades of blue that really don't reflect that amount. And however, we were able to see some trends in that the bottom area of the forest already had a river going through it, and that river is reflected by really low AGB values since trees don't go on rivers. And so we were able to understand that there was a necessity for a more complex model, and one that was based on multiple variables rather than just spatial location.
All right, and in terms of the mathematical methodology that we used here, we fit several spatial models to our response, which is given there by the y based on a vector of covariates given there by the xi. Now, in terms of notation, I'd just like to note that the function of our covariates is just any vector function, and that there would be the ith row of our design matrix, but transposed. The big difference here between your regular regression that you guys have already probably seen and this is the fact that we have correlated errors in this case, as given by those epsilon, that second epsilon term. So we have a white noise process plus a correlated set of errors. Now, our condition in terms of considering a linear predictor of based on our original observations is minimizing the mean squared error of prediction subject to the equivalence of expectation before data is collected. So in terms of the correlation that we chose, you'd expect points that are close together to be to have a high positive correlation, and points that are far apart to have little to no correlation. That's why we choose an exponential structure where that norm is just the distance, the distance in 2 dimensions between 2 points. But we have obviously longitude and latitude measured in meters. Now, if we just denote sigma as sigma 1 squared times the identity plus sigma 2 squared times our correlation matrix, and if we assume that that matrix is positive definite, then we know from our linear algebra courses that it's both invertible and has a Cholesky decomposition. Now, if we multiply our original model equation, which is given by y in vector form is equal to our design matrix times beta plus our error, and I'm just going to write the error as k, so these are all vectors in this matrix. If we multiply by L inverse on this side, L inverse on this side, and L inverse here, right, our covariance matrix is going to be equal to L inverse times sigma, which is L transpose times L inverse transpose, right? And then this just gives the identity matrix, which means we can fit our best linear unbiased predictor based on this beta given over here, just using the same techniques that we would use in basic multiple linear regression. Now, what do we do after that? We now note that this vector of y's is multivariate normal with mean f beta and sigma, which means it has a likelihood function of the form given there, but instead of maximizing that simultaneously, we plug in our MLEs, our MLE of beta, assuming that we know sigma already, and maximize the profile likelihood, which is now just a function of sigma 1 squared, sigma 2 squared, and theta. All right, so after all the math, we get to our results. So we initially set fit an ordinary least squares stepwise regression to help select covariates to use. So that included all possible interactions as the maximum model and just an intercept term as the minimum model. We ended up getting a situation where there were only two-factor interactions included, and we excluded them from our final consideration for the sake of model parsimony. Right? So we included P90, so the 90th percentile of the heights, brightness, greenness, wetness, and our Hansen variable, which is a percentage of tree cover, and of course the last one would be the location, so the x and x1 coordinate and the x2 coordinate, the horizontal coordinate. But first of all, we ran into a problem because there were 51 out of 284 missing P90 values, so we ended up fitting an initial spatial model to impute those P90 values based on the 20 nearest neighbors to each of the missing points. and then we use those imputed P90 values to set up a second spatial model to estimate our AGB in those areas. So now, if you'll recall, P90 is only available from the plane data, so we only have a map of the lines where the plane flew, and we'll get to the full map a little bit later, but in this case, that's a little bit unfortunate. And I'd also like you to note that this model unfortunately fits negative values for AGB in some areas, which is a problem because that is physically impossible. So we also did, Katrina has also made a map of this initial fit, but we'll get to it.
Yeah, so to create something that was a little more aesthetically pleasing, we were actually able to use the leaflet package in R to create a more interactive map, which can be found, it's published here. And so this is again with our first model, so you do see the lines where the LiDAR specifically flew over. I think it's having a little trouble loading right now, but that is published here, and you can see that the leaflet got these satellite imagery from Google Maps to create a more aesthetically pleasing map.
So as we were saying earlier, this only gives a partial map of the region, and our original goal was to create a full continuous map of the area. So we repeated the same analysis, except this time we excluded P90 from our values. We used brightness, greenness, wetness, and our Hansen variables, and included our location coordinates as well, and we end up with this model, which models are quite nice, because as you can see, the location in the very dark blue model the river pretty well, which is exactly where you'd expect there to be little to no above ground biomass.
So the way we can verify that the model is working is by using the data we already know, which is we know the exact AGB for the areas that have been plotted, that have the plots. So if our model can predict the number that the plots give us when we plug in the coordinates, then they should match, and that would indicate we are successful. Another way to verify is we have satellite, our satellite images show the full map in low quality, which we can compare to the map that we constructed using our model.
So the challenges we faced during the project at the very beginning was how to deal with the missing data, but later on we were able to impute it, so that was the problem solved. Another thing we tried to do that was quite challenging was observing the above ground biomass without considering the various tree species. And lastly, we had problem running the data at times due to the large amount of data, and it would take us sometimes 10-15 minutes to run out the data. So ideas for future work: if we had more time, we would have wished to do some cross-validation, that is dividing our data into a training set and a testing set to make sure that our model is quite accurate. And equally, we would have loved to incorporate uncertainty into our various models.
And just a quick note on that, of course that uncertainty can be accounted for based on our code. Of course we get estimates for sigma 1 squared, sigma 2 squared, so we can generate variance estimates for each of the points, because the variance across the diagonal is just sigma 1 squared plus sigma 2 squared. But one of the significant problems is the level of confidence in those points, because you're fitting thousands of points, and if you set them all at a 95% confidence level, you're not actually, you have a problem with multiple testing, right? So in terms of setting that, I believe that would be something that we would have looked into quite heavily, and ended up getting a surface, a lower 95% surface and an upper 95% surface would be something that we would have loved to have gotten into. So anyway, these are just our roles, which of course you can have a look at in terms of what we've posted online. But to conclude, we'd like to obviously thank SAMSI for inviting us out here. This has been a lovely conference. We'd like to thank our director, Dr. Kayan, Dr. Nitschke, who helped us tremendously with the code on his own fields package, Dr. Jones and Thomas Kerman, of course, and of course, who's not here, Dr. Finley, who provided us with our data, and last but not least, of course, Juan, who helped us tremendously as well.
Thank you. Any questions? Yeah.
What was a challenge that the group or individual of you guys overcame? Was there a challenge you guys faced, but you guys still find a way to like execute it and still move on with the project?
Yeah, good question.
Well, I would say that in our group we have a very diligent group of learners, and what we've had here is I'm a senior, but we have rising sophomore, freshman, rising sophomore, and a computer engineer, but she's never used R before. So I was the only one who had used R before because I'm in stats, and essentially we had to learn our roles really quickly. And in terms of coming up with a set of final estimates, I think it was a decent success in terms of that. That was the biggest challenge we had to overcome. Sure.
Okay. Anything else? I had a question. If you think about the Forest Service, and they're trying to decide if they should spend money on these more aircraft overflights or just go with the remotely sensed satellite measurements. Do you have any opinion as to whether or not the aircraft are actually worth the extra expense to determine biomass?
Well, the problem in particular with our model is the fact that we ended up not even using the aircraft data at the end of the day, because the P90 values were only available in those sparse areas, and they ended up only being available at 233 points instead of the original 284 where the actual AGB is recorded. So if I were to make a conclusion off of our analysis, I would say that to go with the satellite data would be a better idea, and to perhaps fund more observations, more individual land observations to get a better spaced out map.
All right.
So this is based on, so for now your validation is based on what you have, like you didn't do the cross validation or anything?
No, unfortunately we didn't end up doing the cross validation.
So for now your results are based on what you have from the satellite right now?
Yes.
Satellite and on-site observations.
So can you please go back to your spatial model?
Oh, for sure.
Yeah.
Okay, this one?
Yeah. Actually, sorry, maybe the one with the circles. Okay, so
Oh, the one with the circles.
did you say yeah, that one? Okay, so what are those circles?
So the circles are actually the points at which we have like absolute data from on-site. So the rest, the spaces in between are just the estimation provided by the spatial model, but those circles itself are the plots that were measured out. So that's why they seem to be different than the surrounding data.
Okay, because I don't know, but I just feel like there's some spots that seem like you might want to smooth out more. It's a little bit, I don't know, but maybe like try around with that.
No, of course we want to smooth that out, but that's what we ended up doing, because this was just a basic preliminary model that we just fit to get a basic look at the map. So obviously the smoothed version is the final map that you saw with the well, this one. The smooth map is this one.
And so what are those blue squiggly lines?
So the blue squiggly lines is where the river is in the region. So you notice that there's 0 above ground biomass in a river, and that's what it predicts.
That also helped us validate our results.
Are there any other questions?
Yeah, Christian?
So the negative numbers, so it's a negative biomass.
Yeah, that's also not possible. That's what I was mentioning on the other model. But the places in which that occurs is flatly on the river. And so unfortunately in those situations it's a modeling error, but it's a modeling error in which we know that the value is already 0. So.
Yeah. That's a good way to answer it. Yeah. All right. Well, let's thank the team again.